Okay. Oops. Forgot to turn the screen up. Okay, so we're doing trigonometry. And so we've seen kind of what the ancient sources of trigonometry were. So basically, it started with the Greeks who wanted to do astronomy. We saw the figure of Hipparchus, who was the first one to try and do some kind of what we would think of as a trig table. And his work then went in two directions. Later on, in the Hellenistic world, it was taken up by Ptolemy, who then refined the chord tables to like a greater degree of precision. And also went to India, where various Sanskrit mathematicians developed sine instead of chord. So as we'll see, sine is just much more easier to deal with chord. When you're dealing with a chord, you always have to halve and double things all the time. Sine takes care of that straight away. Okay, but then the two branches were reunited in Baghdad around the year 800. And it's really the Islamic mathematicians at that time who then really kind of developed it into the modern trig that we have, or they started that. And of course, so just like algebra and arithmetic, it then kind of went to the West later on. So let's talk about the table of chords. So how do we use the table of chords? So if you've got the textbook, they have the first page of Ptolemy's table of chords on page, something like page 157. And so let's look what that table looks like. Okay, let's go to the table. Okay, and I think I have to share this, a different share, I think. Okay. If you click it enough times, it will come. Okay. So here is the table of chords. So it consists of 3 columns. So here's the first, here's the second, and here's the third. So the first column is the arc. And so that's in degrees. So if we have a circle, we have the angle here. So remember that the angle here is both this and it's also this length here. So in these tables, everything is a length. So, so when they talk about an angle, they really mean the corresponding arc length that goes with it. So, and this is in half a degree. So it starts at half a degree. Remember, this is sexagesimal. So that's how they did their fractions back then. And it goes half, 1, 1.5, 2. So every half a degree, from half a degree to 180 degrees. Okay, that's the first column. The second column is this here, and this is the chord. So it is the length of that chord that goes with that arc. Okay, and again, it's in base 60. So remember, this is for a circle with radius equal to 60. So that's what Ptolemy did just to make his computations easier. And then the third column here is what's used for interpolation. Okay, so this is what this tells you is then how much every minute adds to the arc length per minute that you add to the arc. So let's do this by an example. What was the example that I had? 5720. Okay. So let's do 5720. So what is the chord of 57 degrees and 20 minutes? Well, the way that you would do it is it would be the chord of 57 degrees. So you do the biggest half degree, which is smaller than the thing that you're dealing with, plus 20 times the correction. So whatever the correction is for that, for there at 57 degrees. So we go to our table and we look up 57 degrees. Oh, the first page only goes up to 45. Yes, I know it's page. Oh, here we go. So we look for 50 degrees and we find 50 degrees here. So the chord of 50 degrees, oh, no, 57, sorry, degrees. 57 degrees is here, is 57 1533. Okay, so that's the length of the chord. Plus 20 times the correction, and the correction is given right here. It's 55.9. So this is the 0, what does it say? 55.9. Okay, again, so this is minutes, seconds, and thirds.
Does it matter if it's like divided up by commas or anything?
Sorry?
Does it matter if it's divided up by commas?
I'm just doing the commas there just to keep things straight. So I'm using the semicolon as the sexagesimal point, and then I'm just using commas to distinguish minutes from seconds from thirds. Okay. You don't need to put the comma, you could put spaces in right there. Okay, so, and so you want to then have the answer to the nearest second. So you give the correction in thirds, right? But then you're going to be throwing away the thirds and the answer. You just give the thirds there just to give sort of greater accuracy. So we just have to remember our sexagesimal arithmetic. And so we do 20 times that. 20 times 55 is like, what is it, 1,100. And then 20 times 9 is 180. So 180 is 3. Right, 3 times 60, so we go up to here. And then we've got to do 1103 divided by 60. Someone do that for me, please? I don't know what's going to be. 18 and a third. Okay, so this becomes 0, 18 and a third is 20. Okay, so the 20 plus the 33 becomes a 53. 18 plus 15 becomes a 33. And that's how you go about doing it. Okay. Going back to the
Okay, how do I share back? Oh, here we go. Did I do that right? Oh, it's 55.9, not 1. Okay. Okay, so let's do an example of a problem then. Will eventually recognize me, I hope. Okay. So the main thing it was used for, the table of chords, was for solving right triangles. Why is it ignoring me? Okay, so the thing was, the Islamic mathematicians had access both to Ptolemy and the Indian mathematicians. So they used both trig functions. So they used chord and they used sine. And so I think that's why they took the Sanskrit word for chord, and instead of translating it to chord, that would have been confusing to do it with Ptolemy's chord. So they kept the Sanskrit name, and that's what rose to the confusion before. So let's have a look at Nasser al-Din al-Tusi. In the 13th century, he wrote a pretty famous trig book called The Transversal Figure. And in that, he discussed how to use the chord tables to solve right triangles. Okay, so let's say you're given so what do I mean by solving a triangle? So by solving a triangle, I mean that you can give what the length of all the sides are and what all the angles are. Okay, and so if you're given a right triangle, you think, well, what's the minimum amount of information that you need? Well, you can solve it if you're given any two sides. Given any two sides, then you can find the third side using Pythagoras' theorem. And then by using trig, you can solve what the angles are inside. If you're given one side and one acute angle, right? So once you're given an acute angle, you know what the other acute angle is because it's just the complement of that angle. And so since you know the angles, you can then use the chord table to figure out another side. Now you've got two sides. Now you can use Pythagoras' theorem and figure out the third side. So there's kind of two cases there. Let's see. It still doesn't want to play? Okay. Let's have a look at case one. So you're given, this is the one where you're given two sides. Okay. So what you've got to do then is you find the third side using Pythagoras' theorem, and then you recalibrate the right triangle so that the hypotenuse is of length of 120. And if you do that, then you can fit the right triangle into a circle where the hypotenuse is the diameter of the circle. And if the diameter is 120, the radius is 60. So you're in the case of the table of chords. Then you can just look up the length of the recalibrated side in the table of chords, and that will give you your central angle. And then you just appeal to Euclid, book 3, proposition 20, which says that the angle inscribed on a circle is half the central angle. So if this is theta, then this is going to be theta on 2. Or if this is theta, that's going to be 2 theta. Okay, so you can look up Ptolemy, you can find out this central angle, and then you just halve it and you've found the other angle. So let's do an example of that. So let's say we've got a right triangle And we know the legs are 3 and 4. So we all know this one. So we all know that the hypotenuse is 5. Okay, so then we change units and we make 5 120. So that means we have to multiply by 24. And that's what that is in those units. And so we put this into a circle. And we can figure out what that angle is. Okay, and so we go ahead. Oh, I did that too soon. So we go back to our table of chords. Okay, and I want to share that. Okay, so I want to look up 72. So this time, so the whole thing about using tables is you can use tables two-way. Okay, you can look up things. You can look up, have an input and find the output, but you can also go the other way. You can look in the table for the output and find the corresponding input. So that's the thing. So we've got to look in and we've got to find where is there an arc length of 72. It's not there. So we go to the next page and we look and oh, here we find it. We find that 72 lies between 73.30 and 74. So it's 73 degrees 30 minutes, plus it's something extra. Okay, and so how much does it miss out by? So it misses out on 72 degrees by, what is it, 12.5. It's short by 12.5.
Did you get the 12 by 1?
Right, so here, I want 72 degrees. Here I've got 71.47. Is that 55 or 56? Is it 50? Hang on, I've lost myself now. Oh, it is 56, sorry.
Oh, so you would just add to that and then it would
Yeah.
make it, okay.
Yeah, so it's how much short is it by that, and then we can then go to here. So what did I say? Was it 73.30? So it's 50.16 that we want to get there. So how much is that? So we want to, so what did I say it was? 50.16. So we want to do 12.4 divided by 0.5016 to see how many minutes then we have to add. So 12.4 is like what? So that's 12 times 60 is 724. So 724 times 60. And then this is 50 times 60, which is maybe 3016. So what's 724 times 60 divided by 3016? It should be around 15, hopefully.
$13,746.
So that was 724 times 60,
Mhm.
and then you divide by 3016.
I pressed the 0. Give me a sec. 14.4.
14.4. So so let's say 14 minutes. 0.4 is what? It's like 24 seconds. Okay, so we get 73 degrees, 44 minutes, 24 seconds maybe. But that's that angle. And now to get this angle, we halve it. And so half of 73 is what? 36. 3630, half of that is 22, so 52. And we throw away the, whatever, yes, we should throw away the seconds because our table isn't that accurate. Okay, and so now we found this angle is 36 degrees, 52 minutes. And so the last thing to do is to get this angle, which is what? The complement of that is 50 something, isn't it? 53 degrees, 8 minutes. And then, of course, we rub out that to go back to our original triangle, and we've solved the triangle. Okay. Okay, good. I hope I'm still sharing it. Okay, so let's do a problem that they actually would be interested in. So an actual practical problem, finding the parameters of the sun. So we're back in these times, so we know that the sun orbits the Earth in a deferent circle, and so we want to figure out what are the parameters of that. Okay, so remember, here's the picture here. So the Earth is at the center of the universe, and the sun orbits the Earth in a perfect circle with uniform motion. And the center of the sun's orbit is at D, it's offset, so we have this deferent circle, and so we want to figure out what the parameters of the sun is, i.e. we want to solve this little triangle here, which is EDL, where E is the Earth, D is the center of the deferent circle, and L is just the point so that we're making a right triangle here. So what is the information we've got? Well, the reason why the deferent circle came up was because the seasons are of different length. They're not perfectly the same length of each season. So spring is 94.5 days, summer is 92.5 days. And we know that it takes around 365.24 days for the sun to orbit the Earth. So they knew the length of the year fairly accurately by taking precise measurements. So all you've got to do is measure the length of time between summer solstices, for example, to get the length of the solar year. Okay, so here is the model, right? So here is spring, here is summer. So it's kind of weird, right? That the sun is closest to the Earth in autumn, but anyway, that's beside the fact. So here is spring, right? So what happens in spring? Well, in spring, the sun travels this 90 degrees, but it also, because spring is the longest season, it also does this little bit here, which is tau, and this little bit here, which is theta. So 90 plus theta plus tau equals 94.5 days times whatever the uniform speed of the sun is. And we can figure that out, right? Because it travels 360 degrees in a year. So that's 360 divided by that. It's like 59 minutes and 8 seconds per day, or something like And for summer, in summer, it also goes 90 degrees. It does theta, but it's cut off by tau. So we've got two simultaneous equations with two unknowns, and you can solve for that, and you can find out then what these arc lengths are. You then go to your book of chords, and you say, well, here is the sun's circular orbit. Let's say its radius, the distance from the sun to the center of its circle is 60. You do that so that you can use the table of chords. You can then figure out these corresponding arc lengths. And you halve that, and then you've got the legs of the right triangle. So you know two legs of a right triangle, and so you can go ahead and you can solve that, and you can get all the parameters. Okay, so just from this, just by making these sort of solar observations, you can come up with a model for the solar system. And so, for example, you can figure out the eccentricity, which is going to be that distance ED divided by 60. Okay. The other case, given, so the other case is then that you're given a leg plus an angle. And so you then go, given the angle, right, you do this, now you double it to find the central angle, and you look up the chord that it subtends. You find the lengths of the corresponding right triangle, which has hypotenuse 120, and then you rescale back to what your right triangle is. So let's do a problem. So let's calculate the length of the noon shadow of a pole of length 60 at Rhodes at the vernal equinox. Okay. The vernal equinox is the thing that makes it all easy, right? Because here is our right triangle, here is our gnomon. So actually that's where gnomon comes from. It's the thing that sticks out in a sundial. And we're at noon, so the sun is over here, and it's casting a shadow. And this is what we want to find out. This is our x, this is our unknown. And it's the vernal equinox. So that's where the 36 degrees comes in. So that's actually how you can figure out latitude. If at the vernal equinox you shoot the sun at noon, you actually get the actual latitude where you're at. And if it's not the vernal equinox, then you need a whole book of tables to figure out what the correction is to figure out the latitude. So have you ever seen on globes and maps kind of a figure like that? I forget what it's called, but that's the thing that you use to correct for what the latitude is. So sometimes you might see it on a globe, if you're lucky. Anyway.
Dr. Ryan,
Mm-hmm.
what's that symbol on your bottom leg?
Oh, I just call that X just to be modern. Okay. Okay. So this is the shadow. Let's just call it a shadow. Okay, so this is 36 degrees. Okay, and so we actually know what the shadow is, right? We don't. How would we do this in modern terms? We would just say the shadow is 60 times tan of 36. Yeah.
Yeah.
Opposite over hypotenuse multiplied through by. Yeah. So this is, so just remember that this is actually where tan first comes from. it was tan wasn't called tan. We'll see in a moment why it was called tan. Originally, it was called length of the shadow. So yeah, so now this is a right triangle, so we can put it into a circle. And so we can go ahead and what do we want to do? This is 36. This is 54 degrees. Sorry, how do I do this? So I do the center here. So this angle here must be, hang on. I've screwed this up, right? Because I called that 36 and that 54. That's why it looks weird. So this is actually 108 degrees, and this is 72 degrees. Just my bad drawing. I've mixed up acute and obtuse, sorry. And so then you can go ahead and you can look up what, so if this was 120, you could figure out what this was, and you can figure out what this was, and then you can use the fact that it's actually 60 to rescale, and you can go ahead and solve that.
What's the point of the line going through the right angle?
Sorry?
That line, what's the point of it?
So this is the center of the circle.
Okay.
So these are the angles of the triangle. These are the actual angles that you look up in the table.
Oh, those inside angles are the ones that you look up in the table?
Right, because remember the table of chords is the chord from that central angle.
Oh, so with a 72-degree angle, whatever points it touches on the circle, the line
Right, so
through those two
this
points.
length here is chord of 72 degrees. If this was 120 hypotenuse. And so you can go ahead and you can actually go ahead and solve that. So as I said, this is how tangent and cotangent first came about. So the tangent was actually the length of the shadow, and the cotangent was the length of the reversed shadow, or depending upon where your theta was. Okay, so so the Islamic astronomers and mathematicians were actually using trig a lot because it turns out to be very important for them. So they want to figure out things like not only things with astronomy, but they want to figure out, for example, what direction Mecca is. I mean, that's a problem in trigonometry. So it's all to do with angles. So you want a bearing to see which. So there's this whole book of trig tables, which are called that. So that's what you call a collection of trig tables. It's again, it's a Persian word. This time it's a Persian word, and it's the Persian word for chord. And that's, oh, I think that's plural. That's chord in Persian. And so that's what these collection of trig tables were called. And so you not only had trig tables which gave you various trig functions, but also, you know, specialized things that you would need for figuring out things. So like various trig identities where, you know, the latitude of Mecca was plugged into some formula, and it'd be just a whole bunch of tables with that. You know, basically, we'll talk about those kind of things later. So the reason why sine sort of came about was chord was just so, as we've seen, when you're dealing with chord, you've got to halve things, you've got to double things, right? You've got to go from this angle to that angle, so you've got to double it. and you figure out a chord, and then to get the actual length you want to do, you actually want to halve it. So sine just turned out to be much easier to use, and so it's thanks to the Islamic mathematicians that all the 6 trig functions that we know sort of came about. And so again, this is from the transversal figure. He sort of gave all the 6 trig functions as lengths. So we think of trig function as a ratio, like opposite of hypotenuse. That is not, I don't think that came in until like the 17th or 18th century, basically. So but the thing is, you had lots of different sines and cosines and that. It all depended upon the reference circle that you used, right? So it depends upon what the radius of the circle is that you use. So I'm going to just use the convention, putting a little r there. Typically, r was 60. So we can have a look then. So now these things are lengths. So this is sine, this is cosine. Right, we're used to that, right? It's like the x and y coordinate of a circle. Like x squared plus y squared equals r squared. We know that's a parameterization of sine and cosine. Okay, so tan is BD, and now we see why it's called tan. Right, it's called tan because it's the length of the tangent. Okay, cotangent is EK, which is this thing here. Secant is OD, okay, and we see why it's called secant, because it's a secant. And cosecant was KO, was the length of this thing here. So all the trig functions were defined as lengths of various things that came from a circle. And it was all as a function of this arc length here, right? So this arc AB, which we know is really the same thing as this angle here, because any angle gives you an arc, and any arc gives you an angle. So they mentioned all 6 trig functions, but they only gave the tables for 2. They only gave sine and tan. Because the thing is, cosine, cotangent, cosecant, the reason why they're called that is because cosine, for example, is the sine of the complement of the arc. So if you've got a right triangle like this, 36 degrees, the cosine of 36 degrees is the same thing as the sine of 54 degrees. Same with the tangent and cotangent, same with the secant and cosecant. Okay, so you really only need 2 tables. And secant and cosecant were so rarely used, it wasn't worthwhile having tables for them. And so you had trig identities. Okay, so example, tan divided by r is sine divided by cosine. Tan divided by r is r divided by cotangent. Tan divided by secant is sine divided by r. So the fact that you had this reference radius in screwed up all your identities, right? So sine squared plus cosine squared equals r squared. So every trig identity that you know, you have to plug in an r to do that. And it was in the late 10th century that Abu al-Wafa said, hey, if we use r equals 1, it's going to make all our identities much easier. And so people started using r equals 1, but they still used r equals 60 because of Ptolemy. Okay, so it wasn't really until much later that r equals 1. And so that when we let r equals 1, then what they call sine and cosine is what we call sine and cosine. So Abu al-Wafa came up with an addition theorem for sine. Right? So remember I talked about before that Ptolemy had come up with an addition and subtraction formula for chords, and it was what enabled him to be able to make his table of chords. But if you look at it, it's kind of like a horrible formula. And so Abu al-Wafa, his book was called the Zij al-Majisti, right? So Zij means like table of tree, tree table for the Almagest. Calculation of the sine of the sum of two arcs and the sine of their difference when each of them is known. Multiply the sine of each of them by the cosine of the other, expressed in 60ths. And we add the two products if we want the sine of the sum of the two arcs, but take the difference if we want the sine of the difference. So very nice and elegant. Very simple, much simpler than this. Okay, so his formula was also simple because he was using a reference circle of radius 1. So when he says here, expressed in 60ths, that just means that that he's using numbers, because the numbers are in base 60. It's nothing to do with what the reference radius is. And so let's just have a little look at his proof. Right, so let's just look at addition. So you want to look at so you want to figure out what sine of this plus this is. Okay, so what you do then is we kind of drop down this here so that it perpendicular to here, over here. So we get Z, D, T, and H. So BZ here is bisected, and these things sort of bisect these chords. So we get a bunch of similar triangles. In particular, they're similar triangles. And in particular, DZ is going to be half of this thing here. And so basically, this length here gets to the sine of the sum of the angles. Okay? And so then we draw a perpendicular to TH to go to B. And we end up with this guy here. Since we've got right triangles here, that means B, H, O, and T can be put into a circle where BO is going to be the diameter, since we've got little right triangles there. And so then you just look at similar right triangles. Okay, so since you've got similar right triangles, you've got a bunch of relations about ratios of sides. And the interesting thing is, for example, BH, right? If you see what BH is the sine of that arc, right? So because here is the wedge that comes with that arc, and we're dropping down the perpendicular here. So this is sine of BC, and OT, for example, over here, is the cosine of AB. And so from these definitions here, you can come up with expressions for Tn and Hn. These things go here in terms of sine and cosine. And so TH is equal to Tn plus NH. And so then sine of AC is this sum of products here, but we can write these as sines and cosines, and then that gives us the sine, the addition rule for sine. I didn't want to really go into the full detail of that, but the basic idea is setting it up with these similar right triangles. Okay, so that's what I wanted to put on today.